Good afternoon, everybody. I'm Michael Lee. I'm a research scientist here at the Quest for Intelligence. And I work on measuring human behavior. So today I want to tell you about running behavioral experiments on the web with a new Python library we're developing at Quest called NodeKit. But I'm actually going to come at this a bit sideways. Rather than giving you a tutorial that jumps directly into the details of the library and how to use it, I actually want to give a slightly different talk and start from the beginning and ask this more general question, which is how do you actually, starting from scratch, run a web-based human behavioral experiment? And along the way, we're going to span a few slightly more general topics. And to set things up and provide a bit of context for why one would want to learn how to do this, or at least understand how it works, here I'll flash a collection of recent work across a diverse range of topics, from cognitive science to vision, alignment, microecon, and generative AI. And what these works have in common is that the way they achieve their primary result is by utilizing large-scale human behavioral data sets. And you've also, of course, heard work from our previous speakers today, which have used human behavioral data in some form at some scale, for example, psychophysical measurements. And what's sort of behind these works is the growth of web-based behavioral tasks over the past 2 decades. The barrier to entry for people to run behavioral experiments involving people has been greatly reduced since 2005, which is when a platform called Mechanical Turk was released. So here I created a little plot. This is just a very rough and fast plot of the number of Google Scholar hits for Mechanical Turk, which is the name of the original platform for doing this, for psychology versus year. And you can see there's been this just dramatic expansion of growth in the utilization of a platform like this. Prolific is another platform which was released in 2015, also becoming popular. So it's basically never been easier to run behavioral experiments on human beings. You don't even need a dedicated space in the lab anymore. You just need a computer. So it's also very easy to scale. Unlike an in-lab experiment, you don't have to recruit people on an individual basis. You can recruit broadly and internationally. So if you haven't used these platforms before, I just want to go over a few pretty basic facts about how they work. So first, these are platforms where people do tasks in their web browser on their own computers for money. They're also highly scalable. At any given time, there's going to be thousands of people on these platforms. And most tasks are short. Some tasks will last like 2 minutes, and others, on the longer end are maybe an hour at most. Lastly, these are adult participants. There's other platforms like Children Helping Science here at MIT, which are focused on children, if you want to check that out. But these are adult participants. They're anonymous to some extent, and they're drawn from a large, again, international population. So this is less weird, which is an acronym for Western educated, industrial, rich, and democratic participants that you might normally get maybe 3 decades ago. So given this backdrop, I'm going to split what I'm going to talk about today into 2 parts. So one's a bit more conceptual, one's a bit more pragmatic. So in research talks, we often see kind of the finished product of human behavioral experiments, or a nice process data set with a beautiful plot. But today I want to talk a bit more about what goes on behind the scenes and the challenges that a scientist running these tasks needs to solve. And my goal today is to have you come away from this talk sort of better equipped to utilize this for your own research, or at least understand the work of other people. So the first thing I'll talk about is sort of at the design level. So there's no code. This is just about how should we think about designing tasks, particularly for the web context. Secondly, I'll talk a bit more about how do you go from a task design to actually running these tasks. And here I'll weave in this toolkit that we've developed at Quest called NodeKit. Okay, so I'll just jump right into the first part. And I'm going to ground things in a sort of case study. So a particular type of behavior that I want to measure from people on the web. So the task is really simple. You show an image really briefly to a person here for 200 milliseconds, and then ask them, which category of these 8 was present in the image. So that's the task. And we want to collect these sorts of responses across 40 different images of this type. So if you're a modeler, this is like pretty simple and straightforward to think of how to get a model to do this. So just write down some model. Of course, this is really hard and involves training and all that stuff. But just write down a model in computer code that maps images to categories and then just compute. And then you can measure the output of the model sort of like this. This is perhaps the output of a stochastic model that changes its responses every time you query it. And then, of course, just repeat this for every other image that we have. But what about humans? How do we get a human being to sort of compute this function? They're not a computer program. It's a live person that you have to somehow identify and have them actually execute this type of task. So while I'll be talking about this specific task, I hope to say some things that will be useful more broadly. This is just a case study, but one that'll keep things grounded, hopefully. Okay, so let's just start. So how hard could this actually be? So let's imagine we're designing a task for a person who's sitting in front of their computer. So let's say the first thing they'll do is view some instructions that we've written, basically describing what I just told you. And then let's proceed with a trial. And that trial will consist of a couple of phases. So first we'll show a fixation dot. This is a sort of classic visual scientist tool to have the person look at a particular part of the screen. And then we'll show the image for 200 milliseconds. And then finally, we'll present an array of choices, and the person has to click one of them. And let's just repeat this for all the other images that we have. We have 40 in total. And when they're done, let's pay them. So this sounds pretty good to me, but the problem is when you actually run this type of task on the internet, here's what's going to happen. So he's just going to click random buttons until this is over, and he also probably didn't read your instructions. And you're going to pay him anyway, and he's going to go away happy. So in other words, the main problem with this design is that in some sense it's actually optimal for people to skip the instructions than randomly guess. It's lower effort, it's faster, and they get paid the same amount. And that's sort of just a representative failure that is general across running experiments on the web in general. So in short, this has been a problem since the advent of these platforms that people have noticed. And here I'm just showing a handful of recent papers characterizing this issue. So there's ongoing controversy on how bad things really are on platforms like Mechanical Turk and Prolific, but basically anyone you would ask would agree that there is a problem, and it's more pronounced than the in-lab sort of traditional testing context. So it's a little bit tempting at this point, when faced with a data quality issue, to basically blame the participant and kind of dichotomize people into two groups. So there's bad participants who, they don't read your instructions, they love to randomly guess, and they're probably a robot or an AI or something. And then there's good participants. These are people who will read your instructions, give you thoughtful answers, really try to do your task as you intend. But I'm going to argue that this is actually not the best way to think about this issue of data quality. My view is instead that the presence of this dichotomy is really contingent on the design of the task. And put another way, I think well-designed tasks naturally make most of the participants who do this, do the task into a, quote, good participant. And this belief comes from viewing web participants through a perspective where they're performing some sort of optimization problem. So here's a really maybe crude rule of thumb, which is that people on the web, they actively optimize for earnings across time, minus some sort of effort regularization term. So this is sort of a cartoon Homo economicus view. So put another way, if there's a faster and easier way to do the task for the same amount of money, you should assume that someone will figure out how to do it that way, and then they'll actually do it that way, even if it's wrong or actively goes against your instructions. And you can contrast this with the in-lab setting. So let's say I'm walking through, I don't know, the Braden Cognitive Sciences building, and I see a poster for a behavioral task that someone is running. And I'm interested and I want to do the task. If I were recruited, I'd feel sort of a sense of obligation to follow those instructions as closely as possible, and I'd actually feel a little bit bad if I decided midway through to quit the task because it's slightly inconvenient, and I might feel embarrassed if I do poorly on the task, especially if I've met the person who's running the experiment. But things are a little bit different on the web, mainly because of the anonymous and depersonalized nature of the recruitment process, and the fact there are fewer social costs to doing a task poorly. So concretely, where does that lead us? So I'll talk about kind of a two-armed strategy for creating good tasks, and we'll apply it to our little case study. So first, motivated by the view I just shared, it's really important to convince the person that doing the task, quote, correctly, as I, the experimenter, defined, maximizes their earnings per unit time. Secondly, even with these sort of economic incentives, some, quote, bad participants might remain. So we also want to verify the quality of the data. So this sort of second arm is about defining operational measures of data quality, then using them to detect and filter out any remaining bad participants. Okay, so going back to our original task design, what should we actually do at this point to make things better? So the first tweak is really simple, and it's just to add some feedback. So it happens to be the case that in this task, there's always a correct answer that's sort of normatively defined. So here it's obviously the elephant that is the correct answer, and we as the experimenter know ahead of time what the correct answer is. So if they choose the elephant, let's give them a reward or show them a reward screen, which will last here 100 milliseconds. And if they chose anything else, let's make them wait for 1,000 milliseconds, or a second. And that's actually really, really annoying to experience if you do this yourself. You have to just wait and kind of do nothing for a second. Alternatively, we could have used monetary bonuses. So if they got something correct, we could have given them a bit of money, extra money. But here we're going to sort of increase the denominator in the money per time term. So now we can see, if I am a random guesser, soon I'll quickly notice that, just choosing randomly is going to decrease my earnings per unit time. Now, our second tweak is more in line with ARM 2, and we're going to introduce a notion of a catch trial. So a catch trial is just a trial which has an obvious choice. So the assumption is that a participant would only fail on these trials if they weren't doing the task correctly. And by measuring a person's performance on these catch trials, you kind of get an indirect measure of their attentiveness, and this is therefore a measure of data quality. So, so far we've made 2 tweaks. We've added feedback, and now we're mixing in these catch trials. So here we can mix in, I don't know, like 4 or 5 catch trials, kind of randomly. Our third tweak is to add a warm-up block. The idea is that these are trials that would use a separate set of training images, separate from our main set of 40. And here, the idea is to have the participant learn the incentive structure without contaminating, sort of our real data. Okay, so here's sort of a bird's eye view of the task so far. Our last tweak is going to be to introduce a measure of another data quality measure, which is called test-retest reliability. And this is also a really simple concept. It's a very useful trick you can use in your own tasks. Basically, we're just going to repeat some trials from the main block. And the logic here is that if you're randomly guessing, you're only going to agree with your previous answers at chance levels. So in this way, test, retest, agreement rate is another measure of data quality that we're going to use in addition to the cache trials. Okay, so here's what I've told you so far. Two types of maybe approaches to improve data quality. So first is to set up appropriate incentive structures. That's ARM 1. So the first thing we did there was add time-based feedback. Secondly, let's actually introduce measures of data quality and kind of inline them into our task design. The first thing we did there was to mix in these catch trials, which have obvious answers. Thirdly, we added a warm-up block. This is sort of a way to teach the participant that their behavior has consequences, and soon they can learn that and then apply that to your sort of main trials. Lastly, we're using a measure of test-retest reliability in which we repeat trials. And I'll just jump ahead and show you what the task looks like in the web browser. We'll get to this a bit later, but just to give you a sense. All right, so maybe you got the idea. They're doing the warm-up block right now. And at this point, you might fairly be asking me whether this is just a set of my maybe personal superstitions on how to run behavioral tasks, which would be totally fair. It is more of an art than a science. But I ran a little mini experiment for this talk. I recruited 100 people, and I ran a version of the task without feedback. And here on the x-axis, you see our second data quality measure, which is test-retest agreement rate. So farther to the right is better. That dashed vertical line is what you would expect from a random guesser. And you can see that there's this subpopulation of, quote, bad participants that are present in this case, kind of speaking to the dichotomy of subjects that one might conclude exists. But as soon as we add this little tiny micro tweak, which is just making people wait for a second if they get a trial incorrect, you can see that disappears. So this is the same exact population of subjects from which I've taken an independent sample, but now there are no, quote, bad participants. We can do a similar analysis on our other data quality measure, which is catch performance. So here, again, on the x-axis, to the right is better. Dashed line is chance. And once you add feedback, you get way more people who are doing at least the catch trials correctly. So this is going to give you some confidence, additional confidence, that the quality of the data is good. Okay. Last thing I'll show you in terms of the plot is this learning curve. So here in red, that's the warm-up period. So you can see people are kind of absorbing the rules of the task, and therefore the rest of the data is in this more steady state regime. Okay, so I just covered a very narrow slice of the many possible tricks that we have at our disposal for improving data quality. So I'll just mention a few here quickly. So first, there's different ways to incentivize good behavior by sort of altering this incentive landscape. So I already mentioned bonus payments. That's another one. Here we used time, but one could also use additional monetary payments as an alternative. Another is performance-gated blocks, where you kind of force the participant to repeat the task until they reach some criteria on performance. Another more subtle one is you can actually promise participants on these platforms exclusive access to future valuable tasks. My sense is it's sort of a seller's market on these platforms. There are fewer tasks than people would like to do, so that this can be effective. And if you're running a task where there's no notion of correct or incorrect, or if you don't want to deliver normative feedback to your participants, you can also impose payment structures that are based on these sort of meta measures, like data quality. So maybe you'd pay someone more if they have high reliability. And there's also other measures of data quality other than test, retest reliability, and catch performance. One standard one is performing comprehension checks, where you basically quiz the person on their knowledge of the instructions. Another effective approach is to reproduce your task on a narrower set of subjects in sort of gold standard testing conditions in the lab, and just evaluate your web participant similarity to those in-lab subjects. You can think of ways to sort of operationally define data quality in terms of these meta measures like reaction time and straight lining answers, which is basically pressing left 10 times in a row. So I guess what I'd say at this point is there's really no one correct way to do behavioral experiments. It's really about layering on all of these tricks to achieve high data quality for your task. Okay, so I'm also leaving off many other elements of task design which are really important, like randomization and achieving a representative population sample. I'm really focusing on what's unique about the web context. So I told you basically two things. So one, it's really important to convince people that doing the task correctly is going to actually pay off for them. And secondly, one should always inline data quality checks into their task and then use them to monitor and then perhaps filter out the data later. Okay, so the second part of the talk is on implementing and deploying tasks to web participants. So let's just ignore everything we've done so far. Let's just imagine you have some task design that's in your head. It could be the one that we're doing or another one. Concretely, what do you have to do on your computer at this point to get data? And there's basically three things you need to set up. So one, you have to take your task design, sort of abstract task design, and implement it into a web app, which here means a collection of HTML, JavaScript, CSS files, plus all the associated assets that you need. Secondly, you need a way to share that web app with people by uploading it to the public web and a way to store the data that web app generates. Here I'm suggesting S3 and AWS Lambda as one possible solution. And then lastly, you need a way to recruit and actually pay participants by directing them to this web app. So I can talk a little bit about 2 and 3, but I really actually want to focus on component 1, because that's the most error-prone and laborious step in practice, in my experience. So this is the step where you have this design in your head, and you have to turn it into an actual web app. There's certain frameworks that are available for this already that are quite popular, like JSPsych, LabJS, and PsychoPy. But this is actually presenting a lot of friction to people because most scientists, in my experience, they prefer to code in a language like Python or MATLAB. And to use these frameworks, you suddenly have to become a front-end web developer and pick up all these other languages, which can be a really rate-limiting step. So that's why I want to tell you about NodeKit, which is a Python library for behavioral tasks. And the main idea behind NodeKit is that you can represent tasks as graphs, as I have been throughout the talk so far in the figures I've been showing you. So with traditional ways of implementing tasks into web apps, this sort of logical structure of the task is obscured and spread out across many files and lines of code, and even other libraries. When we basically mix in the specification of the task with its implementation. But in NodeKit, a full specification of a task is centralized into a single data structure, which is the graph. And here I'm showing on the right-hand side some example Python code, which is describing this graph on the left. So that's the first piece. NodeKit kind of defines this data type called graph, this nk.graph. And NodeKit has a function which you can call to basically convert this graph representation into a web app. So this is a one-liner, basically. NodeKit also has another important function, which I won't talk about today, which converts a graph into a model simulation environment. So I'll talk now a bit more about the graph data structure and how tasks are represented via this via graphs. So the starting point is, if you think about most behavioral tasks, one can notice sort of a common structure that's shared across many tasks. So first, there's usually a display that shows some stuff, like a piece of text, some images and or some videos that vary across time, perhaps. And then the agent or the participant has to take an action, perhaps within a certain time window. So an example might be they have to select, some number of items. They have to press a key on the keyboard, set a slider value, maybe submit some long-form text, or maybe do nothing and they just have to wait for some time. And then after this happens, the task proceeds to another interaction like this one. So this directly leads to the core building blocks of the NodeKit library. So there's 3 ingredients. The first one is what we call the board. This is just a standardized display system. Secondly is the card. So these are pieces of visual content that unfold across time on the board. Lastly is the sensor. So these are specifications of the set of possible actions that the agent can take before proceeding. So some sensors are the select sensor, the key sensor, text entry, slider, and the wait sensor. And to give you a sense of how building a node looks, a node is just a placement of cards and sensors on the board. So maybe we put an image here, a piece of text right there, and then a text entry field right there. And this node, rendered in the web browser might look something like this. You get the idea. So from these nodes, you can wire them together into graphs. So the simplest graph is just one consisting of a single node. Here's another graph which runs 3 nodes in a row. And graphs can have branches where the next node depends on the agent's action. So I've already shown you this from the first part of the talk. And so from these simple building blocks, which I have designed to be as intuitive as possible, you can actually describe a pretty diverse set of classic psychological tasks. Here I'm just showing you a bunch that are all coded in NodeKit. Of course, one of these might include the task we've been considering so far, which is I've already shown you, so I'll just show it briefly again. So maybe you can imagine how I implemented this task through the use of cards and sensors. Okay, so putting everything together, we started with a task design. We converted it into a web app. Off screen, I uploaded this to S3, and so now people can access it via URL. I created a posting on Mechanical Turk seeking 100 participants. I waited a little bit, and then I downloaded, then analyzed the behavioral data. And the end result is a figure that you might see in a talk like this. So hopefully this gives you a sense of the work it takes to take a measurement of data that's high quality. Okay, so just to wrap up, I told you basically 2 things today. One, let's design an effective task for the web context. Keys there are convincing people that doing the task correctly improves their earnings per unit time. Second, it's really important to inject data quality checks. And secondly, I gave you a very brief overview on what it takes to actually deploy this to the web. So, got to write a web app, upload it, then recruit people from a recruitment platform. So if you're interested, you can check out our GitHub repository. We have NodeKit's GitHub repository link is right here. We have a tutorial on our documentation site which basically implements a task very similar to the one I showed you. And if you have any questions, please feel free to email me. Thank you. Yeah, so for a lot of tasks, you don't have a notion of correct or incorrect. Even in the cases that you're describing, though, I think you as the experimenter, you have some notion of what you want the participant to do in the ideal case. There's some internal concept of data quality that you might carry. One might be, I don't know, if you ask a person to rate a particular LLM response at time point 0, and then you ask them again 10 minutes later. If they're being attentive, if they're doing the task correctly, you might reason that they would give a very similar answer between those two queries that you deliver to them. So you can therefore use sort of internal reliability of that person as a way to compensate them. You can tell them you could be vague or you can be very specific. You can tell them we have ways to evaluate the quality for responses, and maybe under the hood you're measuring test-retest reliability. You can monitor this across time. You can adjust payment scales based on this. So that's one approach I might recommend. You could also use other measures of basically attentiveness. So you might conclude if someone's taking, I don't know, half a second to write a paragraph, you might say, okay, they're probably goofing off, and they're probably just generating nonsense. So you could use that as an alternative metric to filter people out. I think in general, once people kind of understand that, they absorb your intention for what you'd like them to do, and understand if they follow that, they're going to have access to more tasks in the future. I think they can pretty quickly learn to generate high quality data. So it's not there's no one single answer, but these are some of the ways you could think about this problem.
Do you have any thoughts on how to guard against, people using, bots or even agents to do those experiments?
Yeah, that's a really great question and a timely one, given that these agents are getting more and more powerful and sophisticated and cheaper. It's still a little bit unclear. I think people are starting to look at this seriously in recent years. I have a couple of thoughts. So one is you can look at things like raw pointer data. You can look at patterns of how people move the mouse. You can look at reaction time distributions. I would also say that for certain tasks, especially the visual tasks that I've shown you, it's harder for agents to generate, I think, human-like behavior still. I think it's also maybe not worth it. These would require a lot of tokens to solve. But for tasks that are maybe more text-based, where you're simply asking people to, I don't know, write 2 paragraphs about your thoughts on X, there you might see some behaviors where people are copying and pasting your prompt, giving it to ChatGPT, and then pasting it back to the text box. That's totally a possibility. So it's a hard problem. I wish I had a better answer, but I don't know. I think it's still, that's going to be increasingly a problem in the future. I think the gold standard will always be in-lab experiments. So again, you could measure people's behavior in the lab from verified actual humans. And then you could do sort of spot checks of consistency between putative human participant on the web and those in-lab participants. That's another strategy you could consider. All right, well, thank you very much.